There is one last detail related to overfitting we should examine more carefully. We said a dozen times we train the model until the loss function is minimized. We can go on doing that forever, but at some point we'll overfit. That is why we introduced the validation dataset and said a thing or two about breaking the training process. In this lesson, we will explore additional rules that will indicate our model has been trained. The proper term is early stopping. Generally, early stopping is a technique to prevent overfitting. It is called early stopping as we want to stop early, before we overfit, that is. Let's explore the most common ways to do that. The simplest one is to train for a preset number of epochs. In the minimal example after the first section, we trained for 100 epochs. This gave us no guarantee that the minimum has been reached or passed. A high enough learning rate would even cause the loss to diverge to infinity. That's something you should have tried for homework. Still, the problem was so simple that, rookie mistakes aside, very few epochs would cause a satisfactory result. However, our machine learning skills have improved so much, and we shouldn't even consider using this naive method. A bit more sophisticated technique is to stop when the loss function updates become sufficiently small. We even had a note on that when we introduced the gradient descent. A common rule of thumb is to stop when the relative decrease in the loss function becomes less than 0.001 or 0.1%. This simple rule has two underlying ideas. First, we are sure we won't stop before we have reached a minimum. That's because of the way gradient descent works. It will descend until a minimum is reached. The loss function will stop changing, making the update rule yielding in the same weights. In this way, we'll be stuck in the minimum. The second idea is that we want to save computing power by using as few iterations as possible. As we said, once we have reached the minimum or diverged to infinity, we will be stuck there. Knowing that a gazillion more epochs won't change a thing, we can just stop there. This saves us the trouble of iterating uselessly without updating anything. That's obviously a level up from the previous method. While the preset number of epochs approach may ultimately minimize the loss, chances are we can't guess the number of required epochs. Probably the algorithms would have performed thousands of iterations that did not update the weights. Obviously, each epoch that changes nothing is useless and should be dropped. Alright, so the first technique didn't deal with any problems except for minimizing the loss. The second technique optimized the cost and saved computing power, but both can lead to tremendous overfitting. It's only natural that we need a more advanced technique. Yes, we are talking about the validation set strategy. This is the simplest clever technique for early stopping that prevents overfitting. Let me state the rule once again, using the proper figure. A typical training occurs this way. As time goes by, the error becomes smaller. The distribution is exponential, as initially, we are finding better weights quickly. The more we train the model, the harder it gets to achieve an improvement. At some point, it becomes almost flat. Now, if we put the validation curve on the same graph, it would start with the training cost. At the point when we start overfitting, the validation cost will start increasing. Here's the point at which the two functions begin diverging. That's our red flag. We should stop the algorithm before we do more damage to the model. Okay, now, depending on the case, different types of early stopping can be used. The preset number of iterations method was used in the minimal example. That wasn't by chance. The problem was linear and super simple. A more complicated method for early stopping would be a stretch. The second method that monitors the relative change is simple and clever, but doesn't address overfitting. The validation set strategy is simple and cleverer, and it prevents overfitting. However, it may take our algorithm a really long time to overfit. It is possible that the weights are barely moving and we still haven't started overfitting. That's why I like to use a combination of both methods. So, my rule would be: stop when the validation loss starts increasing or when the training loss becomes very small. That's about it. Thanks for watching.